Welcome pre-cal students to class today on this Monday, March 3rd. Hope you guys are doing well. Hope you're ready to learn some math today. There will be a test on this upcoming Monday, so please understand that. And if you're not going to make it to class, I need to know no later than Sunday, please. You do owe me quizzes, so those must be turned in by Tuesday, completely done, all questions asked. So if you have any questions, be sure and get with me on that. And then integrity sheets are called integrity sheets because you are to be men of integrity and tell the truth and be honest. And so make sure you have those completely done when you come into class on Monday. And if you do not, of course, do not take credit for what you don't have done, okay? All right, here we go. Let's grab some paper and pencils here and let's take some notes. First, let me start class today by saying that I made a mistake last week. I taught you on Friday how to find composition of functions. However, did you notice that I did not give you any problems on your homework in which you had to practice composition of functions? Did you notice that? Well, I have to give you some practice problems. You need to practice that. So don't be surprised in today's homework when you notice I have included problems that cover composition of functions, okay? Do not be surprised when that happens. Let me go back a page. So I have to do that because you really need to practice, okay? So in your homework tonight, there will be composition problems. So if you're confused, watch the homework video or go back to Friday's notes and kind of get a little refresher there if you need to, okay? All right, let's get started with today's notes. We're going to be looking at two topics. The first topic deals with the slope of a curved graph. Remember, we have learned how to find the slope of lines, but not curved graphs. I mean, a line is easy. There's a line, there's 2 points, the slope doesn't change the entire time. You just find the rise and you find the run, and you're good. And we've learned how to do that. We've never learned how to find the slope of a curved graph, okay? And we're going to do that today. Now, if you want to, we'll go ahead and copy your heading down. The heading today is called, one of the headings is called Difference Quotients. Difference Quotients, lesson 1.6, and the date today is the 3rd. So 3/3/14, okay? Difference Quotients, lesson 1.6, and March 3rd is the date. Now, you're welcome to turn to page 137 if you would like to. I'm going to very quickly explain to you where we get the formula right here, this formula right here that we're going to be using right here. I'm going to explain that to you. You are not responsible for this information on a test or a quiz, but I do ask that you listen well and hopefully you understand it. If you don't, you can still work the problems out and you'll be fine, but it's very important that I at least attempt to explain to you where we get this formula from. Now, listen to me. If I asked you to find the slope of this curved graph right here, that would really be impossible to do because here the curve is kind of gradual, then it takes off, then it starts to level out and go almost straight up. And so there's really no way to find the exact slope of this curved graph because it's changing. Here it's gradual, here it shoots up quickly. And so the only thing we can do is this. We can pick 2 points on a curved graph and draw what we call a secant line. Now remember, I'm going to go fast. You don't have to understand this. Just do the best that you can, okay? But here's my 2 points. And what I do is I draw a secant line. We call it a secant line through those 2 points. And then if I find the rise over the run of those 2 points, even though the graph kind of did its own little thing, kind of curved up and curved up, it still went from this point to this point. So even though the slope was changing as it went along, in the end, the average slope was whatever this line would be right here, drawn between those 2 points. Now, for some of you, it might make sense. Matthew, Caleb, some of you might not get it, but I still want to go through quickly and explain to you where we get this formula. Okay, so just sit back and watch and try to understand. First of all, I go over an x distance, so I call this x. That's pretty easy. And then from this x, from this tick mark here to this tick mark, the distance is x. So I'm going to call this ordered pair x plus h. Pretty simple. Now, notice if this is x, this ordered pair right here would have an x right here. And then for my y, I'm just going to call it y. So x comma y. But remember, we've learned for y, you can put f of x. And also, it's important that you understand the reason I can put f of x is I have an x right here. So if you have an x here, you can put f of x. If I had a 5 right here, a 5, I would put f of 5 right here. Okay, so far we just pretty much picked some letters, some variables to stand for these two tick marks right here, and there's one ordered pair. Now look at the next ordered pair. I went over x plus h, so I call my x right here x plus h. But remember, if I have an x here, I can put f of x here. Well, if I have x plus h right here, then I can put f of x plus h for my y, which is what I did. So now what I'm going to do is I'm going to use my good old standard y minus y over x minus x to find the slope of this line right here, because remember, the slope of that line passing through these 2 points is the average slope or the average rate of change of this curved graph right here. And I've probably taken too much time already, so going very quickly, if I take y minus y, this whole expression is my y and this whole expression is my y. And so with that in mind, here's my y minus y. This whole expression here is my x, and this whole expression here is my x. So x minus x, y minus y, x minus x. And then if you simplify your denominator, your x's would cancel in the bottom right here in the denominator, and you would end up with this right here. So this is the formula we're going to use to find the slope of a curved graph, okay? This is what we're going to use. So having said that, let me grab a drink here. And that might not have made any sense to you at all. It might have made sense, but we can still look at the problem. So here we go. Let's find the difference quotient for this expression right here using this formula right here. Now, first of all, I have f of x plus h, okay? Forget everything else, please. Forget everything else. I have f of x plus h. That means I'm going to evaluate this function at x plus h. That means everywhere you see an x right here, I'm going to put x plus h. So here's my denominator bar, and I'm going to put 9. Then here's an x. I'm going to put a parentheses, and I'm going to put x plus h, and then plus 5. There. I picked up this whole function right here. I put it right here. The only difference is everywhere there was an x, I put x plus h. Okay? So pretty simple. Not too bad. Now, let's continue on in our formula here. Next, notice in my formula, I have minus f of x. So I put a minus sign and then a parentheses and then f of x. Well, what does f of x equal? F of x equals 9x plus 5, and that's all over h. There we go. It's that simple. So now we're going to simplify the numerator. Take your 9 and multiply it through. 9 times x is 9x. 9 times h is 9h. And then positive 5 is next. And then your negative sign gets multiplied through. So negative 9x, negative 5 all over h. Now watch what happens next. Your positive 9x and your negative 9x would cancel. Your positive 5 and your negative 5 would cancel. And you're left with 9h over h. 9h over h, your h's would cancel, and you did it. You found the difference quotient for this function, and the answer is 9. Now let me explain to you why that makes sense. I kind of tricked you on this one. Let me get a drink here. Remember, looking back at your graph here, your picture, whenever we use this formula right here, it gives us out the average rate of change between 2 points in a given function. Well, notice my function here is linear. I mean, f of x equals, so y equals, look, 9x plus 5. Y is all by itself, so what number's with the x? 9, that's your slope. And what answer did I get out? 9, which makes total sense. Now, it's not going to work like that when you don't have a linear equation. I just wanted to kind of show you that. so you would understand what you're doing. When you use this formula right here, you're getting out an expression that gives you the average rate of change, or the slope. Okay, so using this, let's go ahead and work another problem. Now using this function here, let's go ahead and find the difference quotient. Okay, well, first of all, remember, we cross all this off. Let's just do f of x plus h. That means everywhere there's an x in this expression, I'm going to put x plus h. So 2 parentheses x plus h squared minus parentheses x plus h for this x right here, and then minus 3. Very good. Now the rest of the formula says minus f of x. So minus, and then put a parentheses, and here's your f of x right here, that whole expression. So here we go. And that's your minus f of x, and that's all over h. Now, for the rest of this problem, I'm not going to put the h in the denominator until the very end because it's just a waste of space, okay? I'm just going to keep simplifying my numerator over and over. So first of all, x plus h times x plus h would be x squared plus 2xh plus h squared, okay? Now, next we take our minus sign, we multiply through the parentheses, negative x, negative h. Then bring down your negative 3. And now this negative sign would change all of the signs inside of this parentheses. So your 2x squared becomes a negative 2x squared. Your negative x becomes a positive x, and your negative 3 becomes a positive 3. Now I'm going to get a little sloppy here and try to save time. Actually, what I'm going to do is I'm going to slide this down and kind of get rid of it. Now, see this expression right here? I'm going to go ahead and take this 2 and multiply it through. So 2 times x squared would be 2x squared. 2 times 2xh would be 4xh. And then 2 times h squared would be 2h squared. Positive. Okay? So there we go. And let's go ahead and see if we can erase this just a little bit. Alright, very good. Now, let's see if we can't simplify. I see a positive 2x squared and a negative 2x squared. Okay? I see a negative 3 and a positive 3. I see a negative x and a positive x. So what I'm seeing left is a 4xh, a 2h squared, and a negative h. So let's go ahead and write that down. 4xh plus 2h squared minus h. All over, of course, what's always been in the denominator, and what's always been in the denominator was the variable h. Now, let me go ahead and clear just a little space here so we have some room to work. There we go. And let's get rid of this. Hopefully you've taken notes on all that. Alright, now, I've taught you in the past, you cannot just start crossing things off like this when you have more than one term in the numerator or denominator. And that's true. However, if every single term up top has at least one h and every term in the bottom has at least one h, you can go ahead and do some canceling like that. That's totally acceptable. So I'm going to take one h away from here, one h away from here, one h away from here, so I'm left with an h. Now watch, when I take an h away from here, there's still a negative 1. There was a 1 in front of that h. Don't forget that, please, okay? There's a 1 here, and so when you take that h away, there's still a negative 1. So you end up with 4x from right here plus 2h minus 1 all over 1, and we're not going to put all over 1. So there, you did it. Well, Mr. Earhart, that looks like a really weird slope to me. Yeah, it does. But you know what it's basically saying? What it's basically saying is you can find the slope of the curved graph. And what was the original problem we started off with? Wasn't it this right here? 2x squared minus x minus 3. That's a parabola. If you were to graph that, you get something like this. We can now, look at this, is so cool, students. We can now find the slope of this curve if all that I have is an x right here. Okay, that's all I need is I draw a secant line. I can find the average rate of change from this point to this point as long as I know the x value here. And if I know the x value here, remember h, let's go back to our picture. H is just the difference between one x value and the other x value right here. And so I can find the average rate of change between 2 points on a curved graph as long as I know what 2 points I'm dealing with, as long as I know the x here and the distance between the x and the x here, which would be my h. That's the distance between my two x's. I can substitute those values in and I would get out the slope or the average rate of change. That's really, really, really helpful. You know, this is not easy stuff to understand, but all the details I'm giving you, if you're a little lost or a little fuzzy, everyone, Matthew, Caleb, both you guys, no matter what, can definitely do this. Give me just a second here to clear off the screen. There's not one of you guys, in my opinion, who cannot do the math part here like we did. Okay, you can take this formula and you can practice making your substitutions and then simplifying. Okay, and you'll get some practice tonight in your homework, of course, also. Okay, wrapping this up quickly, one more topic and we're finished. Let's continue on now to our second and final topic of the day. It's pretty easy, guys. It's called X, Y, and origin symmetry. X, Y, and origin symmetry. We're moving on to lesson 1.7, and the date, of course, is still the 3rd, 3/3/14. Now, you take notes however you feel necessary. This is an example of symmetry with respect to the x-axis. Isn't that easy? Just notice this, or we also call it x-axis symmetry. Look, if the graph is symmetrically wrapped around the x-axis, then we call that x-axis symmetry. Notice how it's perfectly wrapped around the x-axis. The distance from here to here is the same from here to here. It's identical, okay? And so we call that x-axis symmetry. By the way, this would not be x-axis symmetry if it was like, here's the x-axis right here, and if the parabola was like this, and then way down here like this. No, that would not be x-axis symmetry. It has to be a mirror reflection right around the x-axis perfectly, okay? And by the way, this next thing I'm going to show you is so important, don't miss this. Whenever you have x-axis symmetry, notice that any ordered pair up here will be the same down here, only the y value changes. So if this point right here is 4, 2, then the point 4, -2 exists on the other side of the graph if you have x-axis symmetry. So what I could do, if I told you a bunch of points, you could find the points down here just by changing the sign of the y value. That'll always be true on x-axis symmetry. Okay, let me say that again. If you have an ordered pair and you have x-axis symmetry, you'll know another ordered pair just like that by changing the sign of the y. That will always be true, okay? So this is a picture of x-axis symmetry. Here is a picture of y-axis symmetry, or we say symmetry with respect to the y-axis. Isn't this easy? Look, it's wrapped around the y-axis perfectly. Piece of cake. So the graphs are easy to recognize. Now notice here, look at this. If I told you 3, 4 existed on this graph, notice over here, if I told you -3, 4 exists, excuse me, then over here 3, 4 would exist. Notice in y-axis symmetry, the x values change signs. So if I told you this point right here existed, whatever that point is, you know the point over here also exists. The only difference is whatever the x value was over here, you would change the sign of it over here. Okay, it's very important you understand that, okay? So in x and y-axis symmetry, the x values, their signs are going to change, okay? All right, so let's continue on. This is a good picture of y-axis symmetry. Now, let's take a look at origin symmetry. The best way to describe origin symmetry is, well, first of all, let's look at the ordered pairs. If you know that an ordered pair exists on a graph and you have origin symmetry or symmetry with respect to the origin, notice the x and the y values both change. So if the ordered pair 3 comma square root of 7 exists, then what that means is the ordered pair negative 3 comma negative square root of 7 also exists. Both signs of that ordered pair would change, okay? And it's very important that you understand that. And my pin's frozen up here. There we go. One more thing I'd like to show you here is, notice when we have x-axis symmetry, it's so easy to recognize it's wrapped around the x-axis. Whenever you have y-axis symmetry, the graph is wrapped around the y-axis. What's a quick way to recognize origin symmetry? Well, if you were to draw an imaginary line through 0, 0, 1, 1, 2, 2, 3, 3, you know, negative 1, negative 1, 2, 2, 3, 3, like that, and draw that line, do you notice how the distance, as you gradually move along the line, it's the same distance here from the curve of the graph to that imaginary line that you drew as it is also right down here. And if you were to draw another line through 0, 0, 1, 1, 2, 2, 3, 3, and then do it like this, I know I'm not drawing a very good line. I apologize. It's really hard to do on this mimeopad. I'll try to do a little better job here. Do you notice how the distance between this line I drew and the graph is the same as the distance here between the line and the graph? So that's another way to recognize origin symmetry, by just looking at the graph. Another way, though, is if they give you ordered pairs, you can also look and see if you have an ordered pair and then the other ordered pair has negative, both of the signs of these numbers are different down here. That's another good way to know you have origin symmetry, okay? So real quick here, in your homework tonight, I'm going to give you graphs to look at and you're going to state what type of symmetry exists. We're not going to practice any of those now, but in your homework tonight, you're going to be looking at some in which you look at a graph like this right here and you decide what type of symmetry it has, or you look at a graph like this, what type of symmetry, or a graph like this, what type of symmetry does it have? Okay, so with that in mind, let's go ahead and do one more thing. Now, looking at graphs and stating what kind of symmetry it has, that's pretty easy, okay, it really is. But what if I give you an equation and I ask you to tell what type of symmetry its graph would have? Well, how would you do this? And I'm glad that you asked. What if I give you the equation, not the graph? How can you know what type of symmetry it has? Well, let me show you here real quick. We're going to look at these three problems real quick and then look, we're finished. Okay, so here we go. Go ahead and write down this first problem. Now, please take some really good notes, okay? To check for x-axis symmetry, everywhere there's a y, not an x, everywhere there's a y, you put a negative y. Everywhere there's a y, you put a negative y. Now what you do next quickly is you simplify and you get y by itself like it was up here. Let me stop and review. We're testing for x-axis symmetry. When you're checking for x-axis symmetry, everywhere there's a y, you put a negative y. Then you simplify. So I've got a negative y. So negative y in parentheses is just negative y. And now we're going to get y by itself. So we make the y positive, but we have to go over here and change all of these signs. Negative x squared and negative 2. In other words, you can go through and change all the signs in an equation as long as you do it to every term. Now, here's what you ask yourself. I put a negative y in for y. I simplified. Did you get out what you started with up here identically? No, you did not. This is y equals x squared plus 2. This is y equals negative x squared minus 2. So this function does not have x-axis symmetry. It does not. Now we're going to quickly check for y-axis. In order to check for y-axis symmetry, everywhere there's an x, you put a parentheses and you substitute a negative x. Now you're going to see this one works, okay? Now here we go. When you square a negative x times a negative x gives you a positive x squared plus 2. So notice I put a negative x in, and after I simplified, I did get what I started with. Okay, I did. And so we do have y-axis symmetry. Let's real quick check for origin symmetry. And you do that by everywhere there's a y, you put a negative y. And everywhere there's an x, you put a negative x. And then you simplify, and hopefully you'll get what you started with. Okay, well, a negative y in parentheses is just negative y. A negative x squared is going to be negative x times negative x squared plus 2, and then go through and change all of your signs to get y by itself, and you do not get what the original problem was. In fact, this would be a negative 2, excuse me. And so we do not have origin symmetry. We did not have x-axis symmetry. This function here has y-axis symmetry. Okay, all right, let's go on to the next problem. We'll do these next two pretty quickly. Okay, for this one right here, we're going to check for x-axis symmetry. So everywhere there's a y, we're going to substitute negative y. And you should see right away this is going to work, because a negative y times negative y times negative y times negative y is a positive y to the fourth equals 4. So when I substituted negative y in, I did get out the original equation. So far, I'll make a little note up here. X-axis symmetry, I'm just going to put x symmetry. Checks, we're good. Now let's check for y-axis symmetry by putting a negative x in everywhere there's an x. And you should see right away this one's going to be just fine, because if you take a negative x squared, negative x times negative x is a positive x squared plus y squared, or excuse me, it should be y to the fourth, I apologize, plus y to the fourth equals y. So yes, I did get out the original problem. So yes, this graph also has y-axis symmetry. And then lastly, we're going to check for x and y symmetry, or in other words, origin symmetry. So everywhere there's an x, I'm going to put a negative x. Everywhere there's a y, I'm going to put a negative y. There we go. Well, when you square a negative x, you get x squared. And when you square, or when you take a negative y times negative y times negative y times negative y, you get a positive y to the fourth equals 4. So this graph here has all of the above. It has x symmetry, x-axis symmetry, y-axis symmetry, and also origin symmetry. Okay, let me grab a drink. We got one more to go and we're finally done. All right, here we go. Okay, I'm back, guys. My computer kind of freaked out there. Here we go. All right, let's go ahead and let's check this function right here for x-axis symmetry, y-axis symmetry, and origin symmetry. Here we go. For x-axis symmetry, everywhere there's a y, I know this is f of x, but for f of x we really have a y. Everywhere there's a y, I'm going to put a negative y. So negative y equals, and then 5x to the 7th minus 6x cubed minus 2x. And of course a negative y in parentheses like this is just a negative y, nothing tricky about that. So I'm going to go through and change all of my signs so y is by itself. And when I do that, students, you should be able to see right away it's not going to work. We do not get out the same original equation we started with right here. So we do not have x-axis symmetry. Now let's check for y-axis symmetry. Let me cross this off. There we go. Everywhere there's an x, I'm going to put a negative x. Okay, so here we go. Y equals 5, and then negative x to the 7th power minus 6, and then negative x to the 3rd power, and then minus 2 parentheses negative x. Okay, now first of all, negative x to the 7th power, negative x times negative x times negative x times negative x over and over will give you a negative x to the 7th times 5. So you would have negative 5x to the 7th. Negative x to the 3rd power, negative x times negative x times negative x would be negative x cubed times 6, which will give you a positive 6x cubed. And then negative 2 times negative x is positive 2x. There is no way in the world that we're getting out what we started with up here. No way. Okay? So we do not have y-axis symmetry. Now let's check for origin symmetry, and we're finally done. Here we go. So where the y is right here, I'm going to substitute a negative y. You're going to be surprised what happens here. And then where the x's are, I'm going to substitute a negative x. There we go. Now, first of all, a negative y in parentheses is just negative y. And of course, a negative x to the 7th power is negative x to the 7th times 5. That's negative 5x to the 7th. Negative x cubed to the 3rd. Negative x times negative x times negative x is negative x cubed times 6 would be a positive 6x cubed. And then a negative, this would be a negative x right here. A negative 2 times the negative x would be a positive 2x. Now, we want to get y by itself. Right now it's a negative y, so we go through and change all the signs. Y becomes positive, 5 becomes positive, 6 becomes negative, and 2x becomes negative. And look at that. We have the exact original equation we started with right up here in the beginning. So we do have origin symmetry. We do. Okay? All right, hopefully you've listened well. I hope these notes have made sense to you. If you have any questions, don't hesitate to call me or email me if you need to. Here's your homework. Let me get a drink here real quick. I've tried to keep this reasonable, of course. I think it's 4, 9, probably about anywhere from 16 to 18 problems, I believe. Okay, so please work on your homework at this time. There's a homework help video to watch if you need to, and call or email if you have any questions.